Yes. Okay, so Professor Jim Dowling, he's an associate professor at the KTH, Royal Institute of Technology.
Yes.
Yeah. So please join me in a warm welcome to Professor Dowling.
Thanks, Jorge. Right, that was a challenge. I learned about, I have a European computer, in case you guessed, so it doesn't work in America. That's, and yesterday, actually, I couldn't get into my hotel because I had to enter in a code, and it sent me an SMS, and a text message, sorry, an American speak, a text message, not an SMS, and it said you can't receive it because you got a European phone. So it's been a good week so far. Okay, so I'm going to do, so I do lecture, right? And I also have a free course called Serverless ML that I ran last autumn, or last fall. And this is based around that course. But this course is also given at KTH over the winter. And I changed the technologies that I used in that course. So in the original one, I used this feature store, Hopsworks, but we also used GitHub Actions, GitHub Pages to build serverless machine learning systems. And then we moved on to using Modal and Hugging Face in the fall or in the winter. But I'm gonna go through what we're doing. What we're trying to do here is build a production machine learning system in only Python, end to end. We'll try and do it in 90 minutes. We've already done this. I've mentioned the course. If you're curious, it's available there. We have a Discord, which we started about 6 weeks ago. We've got about 1,000 people on it already, which is pretty good. And if you want to join along, and I recommend you to join along, what you'll need to do is register an account here at apps.hopsworks.ai. You also can optionally, you don't have to, but it's good if you want to follow on completely, create an account on Modal.ai, and then you'll need to have a user interface. And in fact, Streamlit's probably better than Hugging Face. Hugging Face is fine too, but there's some issues with ports I've discovered in Hugging Face I'll get to later. Now, the slides are available up there as well, so if you want to take a photo of them, you can jump ahead if you think I'm going too slow. And what a serverless machine learning system is going to be, it's going to be layers, right? It's going to have state, and in machine learning, the state that we have are the features. That's the input to the model, the data. So the labels also count as input to your models when you're training. We don't have labels when we're predicting in inference. And then the models themselves. The models themselves are state. And we're going to use Hopsworks for the state. We're going to look at Modal for the compute. And we're going to look at a user interface with either Streamlit. I'm going to show Streamlit first and Hugging Face as well. Now, what we get out of this is a system that runs. Now, all of these different services have very generous free tiers. So I wrote in the abstract, it's a free serverless ML system. There's tons of, I think there's 40 or 50 systems I know of right now running on this stack out there. Unpaywall, welcome. OK, we'll skip that. I don't know what's going on there. OK. Now, actually, what I'm going to do, I'm going to show you before we start. Let's show you what we're going to build. So it's an air quality prediction system. And I actually ran this as the standard project for students who couldn't come up with their own projects at KTH in the winter. And there are tons of really good ones. One in particular in Poland was really nice. But one of my guys just put this together quickly. It's basically you can pick some locations. So we have a bunch here in Seattle. I need to start this running, don't I? OK, now maybe it looks like it's running. OK, and you can see that we're collecting data from Seattle about air quality. And in case you don't know, the internet is full of free sources of data. So one of them is that a lot of people are buying sensors with air quality, and they're connecting to the internet, and you can get those measurements via APIs. So what this service does basically is you can pick some places. I'll pick a few here. I've forgotten to pick some. I'm sorry, this is not my computer, in case you're curious. So let's pick South Park, because sorry, this is me not being able to use a Mac properly. OK. You would think of this. OK, so let's try that one there. Didn't like that. So I'm going to have to. I'm sorry, this is literally clicking on a mouse on the Mac is what's getting me here. OK, so let's go up. Did that one seem to work? Let's delete it, because I'm not sure if it did. OK, Bellevue, I like that one. Let's put some more. Tacoma. We're over in I guess you probably know these places better than I do. But anyway, in any case, we pick some places, and we're going to look at the air quality prediction for the next week. And you can basically pick a bunch of them. So we have Bellevue in here, and you compare it to Seattle. You can see how your place is compared to your neighbors. So this is running free on Streamlit Cloud. It's using the state that's in Hopsworks. And then once a day, we have a feature pipeline running on Modal, which is collecting all the data that came down. All this is running for free. So I don't know, hopefully you can see that there, but basically we've got, this red line is today. So we've got the hindsight predictions, and then we've got the predictions for the next week. And it looks pretty good for air quality. Maybe you want to do hay fever, that would be even better. I think what I say in the course is that there are so many of these potential, I call them prediction services that you could build. It's mind-numbing. One I discovered the other day was a prediction of the NBA games. The NBA playoffs are ongoing there. I thought it was pretty cool. Prediction of football scores, Bitcoin prices, there's tons of them. Okay, so the reason I'm telling you about this is because actually I think the data scientist as we know it today is a little bit endangered species. It's not enough to train models anymore. So if you work at a large organization, and we as a company deal with very large organizations, they've all hired data science teams, they've put them in a room and said, go off and train some models. And there's often walls between the teams. You have like the data analytics team, they give a data dump to the data scientist train a model, they give the model and hand it over the wall to some ops people, like an ML engineer. They're supposed to deploy your model, but they still need to connect it back to the data to get pre-computed features. You end up with, in Conway's law, you basically end up with this type of model. So Conway's law basically says that the systems that you develop will be based around the organizational structures that you have. So in this case, it's incredibly difficult to put models in production. But what it also implies is that as a data scientist, you're only training models here. Right? You're not doing anything else. You're like, my job's training models, that's it. The problem with doing it in this model is that you're only working on static data. You're only working on a dump of data, and you're able to do one-off prediction on that dump of data. It's low business value. Because if you train a model that's making predictions on new data that comes in all the time, and we saw that with our air quality example, there's new data coming in every day. Every day we get new weather predictions. Every day we get new observations of the air quality in these locations. Now we can make predictions for the next 7 days. I don't need to do anything. The system runs by itself. So to do that, I need at least batch data. In that example, I'm using batch data once a day. I have a batch feature pipeline which pulls down the historical observations of air quality, and it also pulls down and scrapes the weather predictions for the next 7 days, and it writes it to our feature store. So this is pretty good. If you want to get to the top of the business value chain, this is TikTok, you're doing real-time data. So as you swipe in TikTok, the events of your swipe, and as you spend time viewing a video, that information gets sent to eventually, ultimately, a Kafka broker. Then you'll have a technology called Flink that processes it, and within a second or two, that event is available in a feature store for the model to use that to make a prediction about what to recommend next. And that's why TikTok is effectively, digital crack for kids, because it's learning in real time about what your preferences are, the last three movies you've watched, how much time you spent on them. That information is available as features when you make a prediction about what to show next. So these, I call them prediction services because we're no longer just training a model. Charles runs this really interesting course on full stack deep learning at Berkeley, and he basically said there in 2017, you needed to build Michelangelo at Uber to do this. This was like an incredible thing. And now you can build these as just a part of a student project. So the students who did these projects did it in 2 weeks. Here we can see user interface for one of the groups. There were 2 in each group. And they basically can show you the predictions of air quality in Poland. So I never got around to doing this for Seattle, but it would be nice to redo this for Seattle. Then you can check your neighbors to see, do you have better air quality than your neighbors this week? But there's a ton of these projects. If you're following the slides, you can click on the link. There's about 25 of them from the class that I gave at KTH. But there's tons of them out on GitHub if you Google around for them. Now, the reason why students are able to build these systems in 2 weeks is because they're building a machine learning system, but we're decomposing it into smaller parts. So what we're not doing is saying, go build a machine learning pipeline, now you have a system. There is no one machine learning pipeline. There's no monolithic machine learning pipeline that is your system, right? A machine learning system that we see in production always consists of 3 parts. So the ML pipelines are, in fact, a feature engineering step. You take raw data and you produce features. You have features and labels, you get models, model training. And then you have features or new input data, new inference data, or new features and models, and you get predictions. So that's basically what you need to build a system. You shouldn't be building the infrastructure. You shouldn't be building, a feature store or a model registry. You should be just using them. So if we can build these 3 different programs, there are going to be 3 Python programs in our example, a feature engineering pipeline, a model training program, an inference program. You're not going to learn state-of-the-art model training in this talk. So if you're here for getting the best model training, probably best to go somewhere else. But what we're going to do is look at how the data can flow easily and how we can build this system without too much effort. If you know Python, if you know pandas, you can get through this very quickly. Right. Any questions at this point? Just shout at me if you have questions or put up your hand. OK, let's keep going. So what we're going to do is write these 3 programs, the feature pipeline, train pipeline, and inference pipeline, to build an air quality prediction service. We need some technology to do that. We'll use Hopsworks as the state layer. I was going to use my laptop, but now I'm on someone else's laptop, and I was going to run Jupyter Notebooks on my laptop. That's how I would normally do it, but unfortunately I couldn't, and I won't be able to run Modal because it's not my laptop here. But I'll show you the code and we'll talk through it. And then you can do a user interface, and in this case I'm using Streamlit as the user interface in Python. There's 2 frameworks that are very popular, Gradio and Streamlit. I did this in Streamlit, and then you can run that on 2 free cloud services. One is Hugging Face Spaces, and the other one is Streamlit Cloud. OK, I mentioned this already. A machine learning system, any machine learning system you build can be built out of these 3 independent machine learning pipelines. The feature pipeline, the training pipeline, and the inference pipeline. All 3 of them have different requirements. So maybe the feature pipeline needs to run once a day. Maybe the inference pipeline needs to run 4 times a day. It's a batch inference pipeline. Maybe the inference pipeline is online. It's an online interactive application that's using a model to make intelligent decisions. So it's an online feature pipeline. Maybe the training pipeline runs once a week, or maybe you only run it when you think the model has degraded. You run it from a Colab notebook. That's totally fine. But what this gives you is the ability to decompose the problem of building a machine learning system, which is a huge challenge, into 3 independent parts that you can work at independently. You can even have different teams doing them. But it's all in Python, so if you're a data scientist working in Python, you should be able to build this. So I've called this a minimal viable prediction service. And what I think basically data scientists should be doing now, when they're talking to their stakeholders and you're presenting your models, is not going and saying, here's my model. I evaluated on this test set. I got 95% accuracy. It's a classification problem. Or here's an F1 score. That says nothing to the stakeholders. You build a service which shows the model living in the ecosystem where it should be built, and you do it iteratively. So you want to get to your first goal should be get to a minimal viable prediction service as fast as possible. Do the absolute minimum. When we're training models, we always talk about baselines. The same is true for feature pipelines and inference pipelines. And the minimum viable prediction service needs to start with a problem that you're trying to solve. So a prediction service or prediction problem. If you're working in industry, often there's business KPIs associated with it. You need to know where the data is coming from, and you have to start at that point on the left. Once you've started on it, your goal is to get to this minimum viable prediction service as fast as possible, and then iteratively improve it. And the consumer could be a user interface, could be a dashboard, it could be a system you're going to integrate with, whatever, it's fine. So we've said there's 3 different pipelines, ML pipelines, feature, training, and inference. This particular system, the air quality prediction system, consists of a feature pipeline, which takes 2 different data sources. One is weather data, and the other is air quality data. And then we have a training pipeline. I've been running up my notebook. Unfortunately, I won't be able to run it now, but we'll look through the code. And then we have a batch inference pipeline. So in fact, I simplified a little bit by removing the batch inference pipeline. The batch inference pipelines generally, they often output for dashboards. So maybe they're going to write to a database, and you'll have a dashboard consuming it from the database. Or maybe you produce images. And I've done that in other projects where you have GitHub pages hosting the dashboard. So the dashboard will get refreshed once per day or once per hour. I did an interesting one on predicting surf heights at a beach in Ireland. And once a day it predicts the new surf heights, and that's a GitHub page. But what I'm going to do is just remove the batch inference pipeline. We'll have an interactive application. And that's the one that we saw earlier. That one is actually being hosted on Streamlit, not on Hugging Face, but they're both effectively equivalent with some caveats. OK, so that's what we're going to do. And a little bit more detail, because the devil's in the detail, obviously. So before, if you remember, what we said was, well, we're going to have these. This is our architecture from before. We said, hey, we've got a feature engineering step. We've got a model training step, and we've got an inference step, and data is being written out there. But like if we see this data here, let's look at that in actual more detail. What are we going to do? Well, firstly, we're going to work in Python only, as we said. We're going to work with pandas. So the feature pipeline is a program which will take the data in, create pandas data frames. We can do some feature engineering in pandas, and then we write the data frame, which contains our features, and in this case also our labels, to a table in the feature store. It's called a feature group. So the API is create pandas data frame, write to the feature group. If you have large volumes of data, you can do this with Spark as well. Our platform also supports Beam and Flink, so there's many different ways you can create features depending on your requirements, but that's the basic of the feature pipeline. The training pipeline will read our features and labels, and it'll train a model, and we'll write the model back to the platform. And then our inference pipeline, it's going to be a small Python program with a UI. It'll download the model, it'll download the data that's going to make predictions with, and then you select your cities, and it makes a prediction for you. And what we can see here is that it's reading the data. The training pipeline, the inference pipeline, are reading data from something called a feature view. Now, what a feature view is it's metadata. There's no state there. It's a selection of features from different feature groups. When you want to create a model, you'll say, I want this feature, this feature, this feature, this feature. And that is your feature view. And one of the problems or challenges of making systems in machine learning is this unified access to data from training and from inference. And this is what the feature view solves that problem for you. It gives you a single API where you can get training data, you can get batch inference data, you can get individual records that you use, or feature vectors as we call them, if you have an online inference model. Okay, the data that we're using, in the course I actually had them subscribing to these services and getting API keys, but we discovered a really cool site, OpenMeteo, that actually gives you some air quality data. Air quality, there's like 20 different measures of air quality. The most common one is called PM25, but OpenMeteo actually gives you PM25 observations. It doesn't give you forecasts. What's interesting as well is that you would think that air quality prediction service, that there's one everywhere, right? You would think like, oh, there must be an air quality prediction service for Seattle. I don't think so. I had a quick Google, I couldn't find one. Some cities like Beijing and Delhi will have them, but very many cities don't. And in particular, what they don't have is it localized to your area. You probably know that if you live in the Sound, there's more wind and the air quality is better, but it'd be nice to have data on that. So this is what the data looks like. This is just a kind of a very, very high-level view of it. You can see we have the top, we have a city name, and then we have a date. So the date is the observation of the weather data. And then we have a bunch of features. And the features here are wind speed max, the direction of the wind, the gust speed max, temperature max. These all have feature types. So some of them are numerical features, some of them are categorical. And then we have this row of features here. It's what we call a feature vector and the individual feature values. So we call this here, this is our primary key, the city name, but we call it the entity ID because each row is uniquely identified by the combination of entity ID and event time. So that's in fact our unique identifier for each row. So that's our weather data, and we get it from, like I said, OpenMeteo. And then we've got the air quality, and the air quality has the same two city name and date. And then we have this PM25, which is our measure of air quality. There are many more air qualities measured out there. But the prediction problem that I have here is I want to predict air quality. So in fact, what I want to do is predict this PM5 value. So this is a regression problem because it's a number. But from a feature store perspective, feature groups contain columns. And this column could be a feature in one model, but it could be a label or a target in another model. So in this case, I'm going to create a feature view that uses that as a label or target. Okay, I mentioned already you get started on creating an account in Hopsworks. We saw that already. Unfortunately, I can't run this code on my laptop, but it's not super complex. I'll open the GitHub repo and we'll have a look at it in a second. What you do basically is you need to, and this is true for Modal. If you're going to try Modal, you'll need to do this as well. I use Conda. You may have another virtual environment you prefer. But basically, 3.9 is what this is tested on. I created an environment, and then I pip installed the requirements in this particular repo. Let's open it, and we'll have a quick look. So this is the repo here. I did add a bunch of requirements just for the UI, but in general, like for the feature pipeline, you only need Hopsworks, and if you're going to use Modal, you'll need Modal client as well. The other ones, GeoPy, are for the UI mostly. JobLib is for the inference pipeline and for the training pipeline. Okay. Yeah, this is the URL up here. It's github.com, Jim Dowling, that's my name, and then air_quality. Okay, so you can open up that repo there. Okay, let's dive in and assume you can do that. So what you'll need to do in Hopsworks, if you create an account, you can use Gmail. It'll take you 10 seconds. Just sign up, click with your Gmail. When it creates, you have to enter a project name. When you've entered a project name, you can click on this user settings up here. You'll need to create an API key. So you need to enter a name in here for the API key. I typically click select all, create the API key, and then save it. Right, so we'll need to save that. And the same is true for Modal. When you use Modal, you create an account. You'll need to pip install the Modal client, so it's modal-client. And then when we use Hopsworks, we'll need to add an API key as an environment variable in Modal. I'll open that later. We'll have a look at it. And then Hugging Face, the same. So Hugging Face, again, it's free. All of these you can register with Gmail. And you need to create what's called a space. So these spaces are user interfaces. You get 2 CPUs and 16 gigabytes of memory, which is really generous. And you're going to create a Streamlit app in this case. So they're the basic preparatory steps that we need to take. We also need to add the Hopsworks API key because our inference pipeline is going to connect to Hopsworks to download the model and the features that we're going to use to score with. Okay, let's get started. We're going to do it's going to be 3 parts. And the first part is the feature pipelines, right? So we're going to write a feature pipeline. Now, maybe I do have ChatGPT here. Writing feature pipelines for modern data sources is super easy if you have a GPT-4 account. I guess most people have used GPT-4 here, right? Yes? ChatGPT. So I do. I have an account here. This is cool. It's logging me in. So no, it's not logging me in. Let's try it out, see if it works. But what I do is I use it for feature pipelines to create code, in fact. And one of the things that, okay, let's see, blah, blah. Okay, is this going to work for me? All right, let's try it. Let's see if we've got GPT-4. It's a little bit better. Yeah. Right. So here's an example of a feature pipeline that I wrote last year. It took me a bit of time. It took me maybe, I'm not the world's best Python programmer. I'm afraid to admit. I'm a systems guy. But it took me a few hours to write this. And I did it in ChatGPT in like 5 minutes. So what I wanted to do was, I'll just pull up the code here. This is I mentioned this already. It predicts wave heights at a beach in Ireland. So this is the beach here. And it was based on an ICML paper that I wrote many years ago. And let's connect this. So this is that's not it here. Actually, it's the web page. Let's go with the hinge. So this is what it does here is this web page once a day. They write out the height of the wave. You can see here it says the wave height is flat. Okay, so that's going to be a problem actually because I had that's what I had to code into my other one. But basically, what I can do is I can say to ChatGPT, please write some Python code. So we can say here, okay, write some Python code to extract the wave height from this URL. And I'll paste in my URL. It didn't kind of work straight off. I'm a bit of a hacker, so I kind of knew that, okay, I can inspect, right? So let's do inspect here. So I can look at this and I can say, okay, where is this? This is inside this particular tag. So it's inside this particular class. So it's inside this class here. So if we copy this, say it's inside the class carousel weather. So I can give it that hint. It is inside the div class. And we paste it in. Okay, so, oh, great. Regenerate response, come on. This works, I promise you. And it's really good. And in fact, it gave me an API that I hadn't used before. And I said, please rewrite this with the requests API, and it did. That's basically how you should be writing your feature pipelines, is my take. If you're doing the kind of thing I'm talking about here, right? So what I'm talking about here are building prediction services for the open internet for people to use for free. If you're working in an enterprise, you'll say, well, hang on, I'm not going to do this in my enterprise, right? This is really hard. But there are tons of GPT tools out there. If you're going to do your feature engineering in SQL, you can say, select the oldest user in this table where the user is from Seattle, and then it'll say select max age from users where location equals Seattle. If you're not great at writing SQL, that'll speed you up quite a lot. So I think this is really useful tools for us to kind of accelerate our development skills. And it means it's going to be easier to build these type of prediction services than it was for me a year ago, which is great. It means we're going to have more of them. Right. So in this case, I said that we have different ways of building these feature pipelines. We can work on static data, or we can have incremental, or what we call batch data. Now, in the database world, or the data world, we call them data pipelines normally. And then we have streaming pipelines, which are the ones that work 24/7 on live data with very low latency. In this case, I'm going to do just static data. So I have actually downloaded a lot of air quality. It's in the repo in a folder called data. And then we're going to have a batch data pipeline, which is going to read, it's going to go and scrape this feature data. And it's going to put it into a pandas data frame and write it to the feature store. OK. So I could probably run it in a Jupyter notebook, actually. But let's try that for the crack, for the laugh, collab. I do know that I have a file in there, actually, so there's a URL that needs to be downloaded. Sorry, it reads a local file. Can you check out a repo in Colab? Anyone know? Collaboratory. OK. We can look at the code in GitHub. Sorry?
You can run a shell command with git clone.
OK. Right. Let's do the following. Let's just go to GitHub and let's look at the code to begin with. If you've got questions, just shout at me. I'll heckle, whatever for your OK, air_quality. There we go. Right. So I said I'd do this in Modal, right? Modal doesn't run notebooks, but notebooks are great for teaching. So we'll have a look at it in the feature pipeline in the notebook, but I also have it written here in Modal. So let's have a quick look through it. In fact, before we look at that, I said there was a static data dump, and then we have the batch feature pipeline. So the static data dump, what I did here is I have this JSON file with all the cities I want to use for the air quality. So I read them up. This is what won't run in my Modal notebook unless I check out the whole repo. So I should download that from the internet. In fact, I did that in the Modal job, because this is the kind of thing you get in Modal. If you run Modal on your laptop, it's going to launch a container in the cloud, right? So in my laptop, I'm running it from my directory. I'm running this Python file, but the Python file reads a local file that's in my directory. And Modal doesn't know about that. So then Modal becomes a little bit more complex. Now you have to mount a shared drive, and you have to do a little bit more. But it's good to know that. So to make it easier, I just downloaded this from a URL. So we've got a bunch of cities. And then I have this backfill data. So I have some historical measurements of this PM5 particulate levels at these cities. And hopefully you can see this, can we? Is that readable? OK, great. And yeah, we're doing pandas, right? So we're going to just read up this historical data into a pandas data frame, df_us. And then we have Seattle here. We have a lot of locations in Seattle. This data is pretty much good to go as it is, because there's not much to it. So you could say, well, for the PM2.5, the spread of values is quite wide. It goes from 0 to up to 1,000 potentially. And you might say, well, I want to encode that. So that's something that comes up again and again with feature stores. Should I encode these values before I write them to the feature store, or should I do it in the training pipeline? Well, the answer is you do it in the training pipeline. You don't do it when you're writing to the feature store. And the reason why is because when you encode a value, so if you have a numerical feature and you're normalizing it or standardizing it, if you've got a categorical feature and you're one-hot encoding it, you have a reference set of data that you need to use to encode those values. So if I'm encoding a numerical feature and I've got a batch of data, I've got today's data that I want to encode, what am I encoding it against? The existing data in the feature group in the table? I'm going to read up all that data, calculate the mean, calculate standard deviation, now standardize, right? Now write it to the feature store. Oh, whoops, I have to rewrite all the other values that are in there already because, hey, the mean and standard deviation have changed, right? So what that means is that your feature pipelines will get slower and slower. There's going to be this write amplification. That's not good, right? However, when you're training a model, you take a snapshot of data. So you're taking a snapshot of data. If it's time series data, it's pretty clear it's going to be this. If it's not time series data, take all the data in the feature tables or feature groups. Fine, but it's a reference of data. So now when we encode the values with respect to that reference data set, well, that's fine. If we have new data coming in on our online inference pipeline and we need to encode those, well, we know the statistics for this training data set. It's a reference snapshot. So we can then encode them. And in practice, that means scikit-learn pipelines, if you like scikit-learn, or pre-processing pipelines in Keras. In our feature view, we also support transformations, so we store that metadata, and you can just say, hey, encode these feature values for me. So that's done in training and inference pipelines, not in feature pipelines. OK, so this is not doing too much. It's basically getting our air quality data, getting our weather data. We've got a lot more features we can see here in weather. I don't know if we need all of those. Rainfall does affect air quality, so probably there's some predictive power in it. And basically, the feature store, all we do, maybe if I can zoom in a tiny bit, maybe a little bit there, yeah? Did that work? I'm scared to touch it. Yeah, we just basically log into the platform. Now, it'll prompt you for the API key, and you can paste it in, or you can set environment variables, so you don't have to enter it every time. Now, what I did as well, and this is, it's getting much easier to do this compared to how you have done it before. But how do I validate the data before it's written in? Garbage in, garbage out. I'm scraping data from the internet. If I scrape PM25 values and they're negative, or maybe they're greater than 1,000, they're obviously nonsense. So what we can do is we can define an expectation in Great Expectations to say, hey, check all the PM25 values, make sure they're in this expected range. And if they're not, the feature pipeline will fail, or we'll let the data go in, and we can then inspect it and say, hey, we'll remove that. And so that's what's going to happen here. The feature store will actually do this for us, because we just basically, when we're creating this feature group, we say this is the expectation suite. So every time you're writing, apply these expectations before we write it to the actual feature store. Now, this is our feature group. And the reason why you can think of it as a table, right? It's a feature table. The reason why we call it a group rather than a table is because the data will be available both for batch API access, so large volumes of it, but also for low latency access. And in fact, in feature stores, that data is replicated in two different databases. You've got a columnar one, which has low cost storage with efficient batch access, and then you've got a low latency key value or row-oriented database where you can retrieve feature vectors very efficiently for your online applications. So the data can be in these two tables. So we don't call it one table; it's a group. It could be one table. It could be just offline. In this case, it's only offline, but it can also be online, depending on the type of model you're training. So all I have to do when I want to insert my data frame here, I'm inserting the data frame here, is I create the feature group, and I can put some metadata in here: the name, the description. We have versioning. It's very important for ML ops. If you don't have versions for things like feature groups and you want to make a schema breaking change, how do you do it? How do you manage the pipelines for the old version of the model that use these features and the new version that use the new features? So this is really important. And then we have the primary key, which uniquely identifies each row, and the event time, which is basically the observation time for these features in this table. So basically it uploads it there, and then we do the same for our weather data. We can also add metadata descriptions of individual features like I did here, and then we insert our weather data here. Right, so let's have a look at what that looks like once we've inserted it. This is Hopsworks here. I'm running a new version, like the version that if you've registered at hopsworks.ai, it'll be on 3.0. This is 3.2, but there's only minor changes. So these are my two feature groups that appeared. So let's look at the air quality one first. So you can see here there's 4 features. We've got city name, date, PM25, and then Unix time, which I don't know if I actually need it. I'll probably remove it. And the Unix time is also the event time. So you can insert pandas date times, that's fine, or you can have strings. We can see how this feature group is used. It's used in these 4 different training data sets by this feature view later on. I didn't run the expectations on this earlier, but you would have your expectation results in here, and then you can have tags and alerts and so on. So what you get out of the box that's nice for free is you can kind of preview your data so you can see what's in there. So here we're going to have a quick look at the data. So basically, really trivial EDA, right? So for example, if I want to design my rule for what's a valid range of PM5 values, well, I can go down here and say what the min was -3. That's not so good. And the max was 476. So I don't know how you have a -3 of PM5, 2.5, but there's some garbage in there right now. OK. And then the same is true for our weather feature group, which was here. That one got written in there. Any questions on any of this? This is all pretty straightforward, right? Yeah. OK. Cool. So that's our feature pipeline. And I kind of went through a bunch of it already. We need to schedule it to run. So we like to run on a schedule. It's not enough just to run it once in your notebook. What kind of things can you do in the feature pipeline? I won't have time to go through all of these, but what is feature engineering, right? You can compute aggregates, binning, filtering, lag features. I mean, there's a ton of different things you can do. There's new things the whole time. And that really, honestly, that's the power of Python, right? There are libraries for all of this in Python. So, I hear, at least in the enterprise space, that SQL is the language for feature engineering. But there's just so many things that you can't do in SQL yet. And even Spark it doesn't always have these capabilities, PySpark. I mentioned this already. Generally, the features are not encoded in our feature pipeline. So I did mention that, there are many ways of writing feature pipelines. So often, if you have huge volumes of data, SQL and Snowflake, and your data's in Snowflake, that's the best way to go. It's very good for aggregations and things like that. Today, we're going to just do pandas. Pandas 2 is great. You can handle larger volumes of data. Polar's even better. But you get to a certain data volume where even Polars won't really work for you. I put this at 100 gigabytes. Maybe it's a bit more, but it's not at terabytes. When you get to terabytes, you need to go to either a data warehouse or to Spark. You can also use Flink or Spark Streaming, which are streaming pipelines. They're a little bit more challenging, but what you get is fresher features. And fresher features may be important for your particular prediction problem, or may not be. OK. We looked at this already. This is the code to create our feature group and how to insert our feature. That's pretty straightforward, and we insert our 2 feature groups. That's pretty OK. And what we didn't look at were how do I do my feature functions? How do I do my feature engineering in pandas? Typically, what we would say is it's good practice to define individual functions to compute individual features. Now, there's a guy called Stefan here he has a startup based on a framework called Hamilton. And Hamilton has this encoded in its principles, that if you can encapsulate the computation of a feature into an individual function, then teams can easily work on the feature computation in parallel. You can individually test each feature. So you can have unit tests in particular. So if someone were to change the implementation of a feature and change how the feature is computed, that's bad, right? Because that's going to change the data, the feature that's available. So you would like to warn people with unit tests, hang on, you can't change, there's a contract for that feature. And when you change it, then it's going to break, it's going to be incompatible feature data with the data that's already in our feature group. So a good way of doing this is to define your feature functions as UDFs, user-defined functions in a module. Typically what we would do is we would say the feature group name, air quality, in a package called features, put the features as individual names there, and then we can also use those feature functions in our online inference pipelines if we need to compute these features in our online inference pipeline. We use the same code. All right, let's have a look at how we schedule this feature pipeline then. This is the code for Modal. This is basically all you need, right? It's not more complex than this. So some of the things that Modal solves, which are really, really great and very easy, are here we can see that we've got an image, right, a container. So if you're using a data science platform, like maybe you've used SageMaker or something like that, they have these pre-made images. Like, so you pick that one, or I'll have that one. Well, hang on, I want this other library. How do I add it to my image? Well, you have to kind of build your own image. You have to write a Docker file. You have to compile it. You have to upload it. You lose a day of work, right? In Modal, you can just pick your image, Debian Slim. I can pick different versions. I can pip install libraries. I can, apt install dependencies or packages that I need. It's really, really great. And in fact, Modal do the same, Hugging Face do the same for Hugging Face spaces. You can have custom Docker images, and then you can pip install any libraries that are in the requirements.txt file. Hugging Face is going to just install them. So the other thing that Modal gives you, which is really nice, is the ability to schedule these pipelines to run at a cadence. So in this case, we want to run this pipeline once every day. And all I have to do is annotate the function that I'm going to call with this stub.function call. And I say the image. This is our Linux image with this library Hopsworks installed. And it's going to run once a day. And I also need an API key. So I need this Hopsworks API key in order to connect to Hopsworks to write my data frames to the feature store. Well, I can get that from Modal here, from this particular line of code. And then all I have to do down here in my main, I'm saying deploy this as the air quality daily. Now, the reason why I've got all of this weird stuff, say with stub.run g and so on, you basically encapsulate your code into this function. So I put all of my feature engineering code into this function g. Now, one thing I noticed straight off when I was doing this with the students, Eric, who developed this, gave a talk for them. And they like it. They're kind of like it's a little bit hard, but not too bad. But what they found a little bit more challenging was that, you don't always have internet access. Modal is super fast. I'd love to show you a demo where it just runs that Python code and gives you the logs in Python in 5 seconds. But as it's not my laptop, I can't. But let's have a look at the code. And one of the things that it's a feature request that's always going on there, which is that you'd like to be able to run the code locally, and they currently don't support it. So I hacked it out for the course. And I basically set this environment, or this parameter local false. So if you set local false, that means it's running a Modal. If you set local true, it'll just run on your laptop. So then you have this little hack which says if local's false, well, then we do the Modal stuff. And Modal will just call this function g. So g is doing the actual work down here. So this is g here. But if I'm in local mode, I just call g. Right. So it'll run on my local laptop, and I can try it out, and then I can schedule the thing to run in Modal when I'm happy with it. So I find that a really good way of working. It's pretty. It feels like normal Python pandas development. It really shortens your iteration cycle for developing things and putting them into. In this case, we use the term into production, which is effectively what we're doing. Right. We shouldn't be shy about it. If you're building oh god, let me see if this works. That's me. That looks like me. Oh god, here we go. Phone. Everyone is like, oh no, maybe I have a European phone. Will it allow my European text message to get through? Yes, it worked. I like the way that they actually automatically press the button, but what really annoys me is that they don't autofocus on the window, right? Does anyone else get really annoyed by that? Why don't they autofocus on it? Because I have to click on it to get... All right. Pet peeves. So this is my air quality app. This is what it looks like on Modal here. Like, I run it like next run in 18 hours, blah, blah, blah. The one I was running in the course was Iris Daily, totally mad, and I ran lots of times. You can see you get your logs. It's nice. You can just go look at your logs for a run and see, no logs. It removed them all. Thank you. Okay, but it's really nice, right? So it's really trivial to get started. You can create a new secret. You put your API key in there. It's an environment variable, and then off you go. If you're doing data engineering and you're building kind of complex, you're used to building complex DAGs and Airflow and running these things and scheduling them. Often our feature pipelines are not as complex as building many different data sets that are consumed by different BI tools. So I find that Modal generally is good enough for a lot of these potential use cases. Right, so that's Modal, and that thing can run. And the other one that I mentioned is GitHub Actions. You can also do the same thing in GitHub Actions. If you're interested, go to the serverless ML course that I gave, where we use GitHub Actions. It's free. That's the benefit of GitHub as well, of course. There's a little bit more work to do. It's not as nice. Yeah, so in Modal, you're basically defining your dependencies, the image you want, the libraries you want, the environment variables, and then you run the thing. It's pretty straightforward. If you're to do in GitHub Actions, this is kind of what it looks like. This was my version because it doesn't give you stuff for free in GitHub Actions. So what I do is I install a Python version, I install my pip install my requirements, I set an environment variable, which is the Hopsworks API key, and then when I want to run my notebook, I just run nbconvert. So I had to add nbconvert to my requirements.txt, and it'll convert my notebook into a Python program and run it. Because my Python notebook runs as 95% of Python notebooks do from top to bottom. You just run it from top to bottom. So that's pretty okay. Excuse me. Honestly, I think you can do training pipelines this way. So, you know, a lot of us love to do training in notebooks because we want to do analytics of the model with the notebook when we've trained it. And I don't see the harm in running these things as training pipelines on a schedule. I don't know. There are biases that you know, many engineers have against notebooks in that case. But I think for training pipelines, this is often good enough. I covered this already, so I won't go through it anymore. Great expectations. And what it looks like is you get in your feature group, you'll see all these different runs. Just we saw the runs in Modal, we can see the results of our expectations. And you can get an alert, you know, send a Slack message if there's a problem or something like that. So that's number one covered, which was feature pipelines. Now we're going to do training pipelines. This is the easy part. Training pipelines are pretty straightforward. The thing that you want to do when you've got a feature store and it's got tons of features, like Uber say they have 50,000 features in their feature store, which is quite a lot. What you need to do at that point is you're not always going to create novel features for your prediction problem. There may be existing features there for you. I think in the near future there's going to be feature marts. It's a term we're using internally, where you can get many of these existing features, and it won't always be that you have to create new feature pipelines from scratch. But when you're selecting features, if you have some available, some of the things you should consider is, okay, is this a useful feature for my prediction problem? Does it have predictive power? Is it redundant? Is there one like that there already? I don't need it. Is it irrelevant? If I'm working in industry, of course, I care about, and not just in industry, if you've ethically challenged, you should care anyway. Is this okay to use this feature? And then the other one that I think stumps a lot of people who don't have a systems background is this feasible to use this feature? Can I compute it in my online application? Because that's often a source of tension in many organizations. You know, you'll have a feature that you'll say, okay, I know this it's going to be user input. It's going to be a string, and I want to encode it with this one hot encoding pipeline that scikit-learn is using. Will that be okay? And the answer is yes, of course. But if you want to use that feature using a feature store like Hopsworks, you would look at the feature group and say, is that feature available online? You know, if it's available online, then yeah, sure, it'll go straight off. If it's not, well, then it depends on the model. We'll see how it goes. So the process of selecting features, or feature selection, is really just going to these different tables, saying I would like this feature, join them together, and boom, I've got this feature view. If you're a data warehousing person, and is there any data warehousing people here? Dimensional modeling? No. Do you know what? In the course, in the serverless ML course, I gave part of the course was on data modeling, because we don't do enough data modeling. I did work at MySQL before, but data modeling is very inherent because most data scientists at enterprises work with data from data warehouses. It's been modeled into, you know, either Kimball or Bill Inman's model. It's got fact tables, it's got dimension tables, and you probably heard those words and you're thinking, I have no idea what they are, but they're basically what is a fact is for us a label. So a label is the target, the outcome, in this case the air quality. It has a timestamp, so TS is timestamp, and what I want are features at the same timestamp. So what was the air quality? Sorry, what was the wind speed? What was the wind direction? What was the temperature? You know, what was their precipitation at the time? I'm joining those together because they're the features I'm going to use as input to this model where I'm predicting the label or target, in this case, which is the PM5 value. So this is a fact dimension model, and it's not super hard, right? This is actually really easy stuff. Okay, so in this case, my target is in the air quality feature group, is the PM5 column. I need to join that with the other weather column. Luckily enough, I have the city name is the same, and I need the same date. And that's going to give me the feature view, right? But there's a little bit more to creating a feature view than just selecting the features. Selecting is obviously the most important one. You might want to say, what's the target column? We use the term label. I prefer target, but whatever. I didn't win that debate. You can filter out data. You can say, well, I'm only going to work with data in Seattle, so we'll only have data in this particular feature view for Seattle. And then you can also add model-specific encodings. So encodings for models that use this particular feature view. So you might say, well, encode the wind speed max with a min-max scalar. I'm going to use scikit-learn pipelines instead of using the transformations in feature views, but both of them are valid ways of doing it. Now, the value of a feature view is that it's a unified API for training and inference. That's the value. That's the hard thing that's really hard. How do I make sure this feature is usable? How do I create batch inference data? How do I create online inference data and training data from the same set of features, the same selection of features that I want to use? So the feature view is really a model view, if you will. It's the input to the model. It's a set of features that will be input to the model for training, but also for inference. And you may have heard terms like training serving skew or online offline skew. And I had a little debate with someone on Twitter recently, and he was like, yeah, you get this type of skew. You forgot the type of skew where you're using a feature when you're training, but then you didn't use it in the inference. And I said, what are you talking about? Because I've been working with feature stores for quite a while. I'm like, you have the feature view. That has a set of features. If I'm in inference and I don't have that feature available, I'll see it, because it won't be available in my feature view. Because that's what's available online. It tells me in advance. It's the contract. Okay. So how do I create the feature view? Well, I basically get references to my two feature groups in this case, and then I select features from them. So I'm selecting only the PM25 from my air quality, but I'm joining it with all the features in the weather group. Now, there is internally there's an optimizer, query optimizer, which knows that the primary keys are common, that we have this city name in both of the feature groups, so it will join on those, and also the date. And this does something more complex called a point-in-time correct join, which I won't get into too much details, but it basically means that we don't want to have any future data leakage. We don't want to have, for example, the PM25 label having weather values in the future. So we want to have them as the weather values, or weather feature values, being at the same time as the PM25 value was observed. So the feature view is basically this selection of features here, and we decide what the label is, and give it a description and a name and a version. So it looks like a table, right? It's just a table. But remember, the data is not being stored. It's just metadata. We don't actually make a copy of any of the data. So what you can do with the feature view is you can say, hey, I want to create some training data. And here's a start time and an end time. And we get training data set version 1. A week later, there's more data has arrived, because the feature pipeline keeps running every day. So I say, give me more training data V2. And I train model V2. And then I say, okay, I've got model V2. I'm going to get some data to make predictions with, to predict what the air quality will be. And so I get batch inference data. I say, feature view.get batch data. And maybe then I have an online model which says, I only want the row for Portland. Give me the current features for Portland's weather, and I'll make a prediction of the air quality with that. That would be an online model. So the feature view allows you to create these snapshots of data, training data or inference data, whether it's batch inference or online inference. And you can think of it looking like this, kind of from a conceptual perspective, that the data is coming in from the left and it's filling up over time. And when you train models, you have like a snapshot of data over a time window. And then this doesn't imply all these problems are time series problems, but you basically collect data up to a certain point in time, you train a model, and then the model makes predictions on data that arrives after that point in time. Now, one thing that feature views, they can have, at least in the Hopsworks platform, you can have transformations associated with. So if you know the feature type, if you know that this is a numerical feature, well then I can use min-max scalar, or I can use a standardizer. So this is normalizing the feature value. This one is using the ordinal encoder. So this is a categorical feature with unordered values. If I have ordered values, I might use the label encoder, or I might use the one-hot encoder if I care about data size, data volume. And maybe in a feed-forward network, I'd need to have numerical features for everything. So I need to obviously encode my categorical feature, and I'd like to have Gaussian distributed features for the rest so that the feed-forward network works well. XGBoost won't care about that, so all I need to do is encode the categorical feature, and maybe logistic regression will want them back in. So depending on your model, if you're to do the transformations in the feature view, then you would have to have different feature views for all of these. The other alternative is just to use sklearn pipelines and then have different training pipelines, one for these 3 different models of feed-forward, XGBoost, and logistic regression. And then we're going to save the pipeline object with our model. And that's what I'm going to do in this example here. So this is our training pipeline. I'll just show you the code because the notebook's a little bit longer. It's not too long. So here's what's cool about the feature view. It's scikit-learn, right? I just call train test split, and I give it a test side, and I get back my train set of features, my test set of features, my train set of labels, and my test set of labels. And now I can go ahead and say, OK, I'm going to encode the, in this case, all right, it's missing the for loop here, but it's basically going to encode any categorical features in there. And this, so this is our preprocessor. It's going to apply the categorical transformer to any columns that are categorical variables. It's going to do, the one hot encoder is the transformer. And then it's going to train the model with XGBoost regressor. So all we call is CLF, which is our pipeline object. We call train. We call it. We fit it to the training set of features, and we pass it then the training set of labels, and we now have a trained model. So this is basically an entire training pipeline. There's not too much to it. Once you have the features in your feature store and you've created a feature view, it's pretty straightforward. So once you've trained your model, we need to save it because we want to have an inference pipelines coming after it. So in this case, we're using Hopsworks feature view because it's our feature model registry. Sorry, because it's easy to use. You can use other platforms out there like MLflow, which is pretty good, but it's not serverless. If you want to use a serverless model registry, other ones, weights and biases have one. There's some notebooks showing you how to use weights and biases model registry. I think it's a little bit more complex. In this case, what we do is we basically serialize the pipeline object using joblib. We then get the schema for our model using the, in this case, the features and the labels. It doesn't matter if you pass in the training or test sets here, because they both are the same set of features. And then we can even store, if I evaluate the model on the test set and I get an accuracy, or in this case it's a regression problem, so it shouldn't be accuracy. If we get some loss, some kind of loss metric in here, we can store it. We can also store an input example. So if we deploy the model, we'll get an immediate example of features that you can just press test the model if you're deploying it as a service, as a model deployment on model serving infra. And then you say the schema to the model. And then you basically save this directory. So when you save the model, you can also stick in images in there so that they'll all appear in the model registry, so you can see the performance of the model and so on. And that's kind of a nice way of doing it. So let's have a look at that in code. And we'll look at it in the platform first, actually. I need to go to change it to data science profile here. OK, so this is the model I trained earlier, air quality XGBoost. You can see there's some, so the metrics here were the root mean squared error and the mean squared error, and we had R squared loss, so we can see then the schema and so on. So you can also have a look at the model files. I think I saved an image with this. Yes, the residual errors. So the notebook computed these, not great. There's another version of this tutorial in our in Hopsworks tutorials, which gives you better performance. This was me hacking it out. I want to make it a little bit easier to read. But let's look at that actual notebook then. Has anyone got questions? Just shout at me. I'm going 100 miles an hour here. OK. So this is it here. It's the training and data set and modeling. So this notebook is going to, we can see here we install a bunch of visualization libraries as well, because we're going to do evaluation in here as well. But we connect to the feature store. We get reference to our feature groups. We create, we select the features from those feature groups into this object called a query object. You can read data and sort of have a look at it to see what the data will look like from that feature view and inspect it before you actually go ahead and create the feature view. If you're using the managed version that I mentioned at the beginning, app.hopsworks.ai, it's on Hopsworks 3.0, so you'll have to uncomment this line and comment out this line, because this get or create is only from 3.1. But I ran it here. So it'll either get or create the feature view, and then we can go ahead and get some training data. So here we're getting our training data back as pandas data frames. So we've got these 4 pandas data frames for the training and test set, the features and labels. You can also create, if you've got a large volume of data from pandas, you can also say create training data as files. So it can be CSV or Parquet or TF record. And even if it's like terabytes of data, you can still do it from your Python notebook, because what will happen is it'll kick off a Spark job in the back end that will do this point-in-time correct join and write the data out to wherever you want to write it to. So it could be to an S3 bucket or to the file system in our platform. OK, so just have a quick look at what came out there. Oh, Mac is hitting me here. I don't like Macs. Never liked them. No offense. You're OK. You're in Washington. You're not I'm not in California now, right? We're a safe space, is it? I hope. OK. God, see, it did me again. All right. I actually have this problem a lot with my students. I'm going like, oh, geez, Mac. I get like some sort of post-traumatic trauma that I have to use the Mac. So yeah, this is the code we looked at earlier. It's training the model. We're computing our metrics, just doing some plotting of the feature importance and things like that. And then we save our model. So we get a reference to the model registry and then save it there. So that's basically our training pipeline, not too much else. You can do, I wouldn't normally do this in the same notebook, but you can try it out then. I'd test it at the end just to see how things were working, make some predictions on a batch of data. But you don't need necessarily to do that. So that's the training pipeline. So I've got inference left. Any questions on that? No? All right, I'm gonna get this one done, and then we'll come a little bit on the principles of MLOps, and then we're done. Then you can go ahead and go build one of these things. So there are different types of inference pipelines. There's basically 3 different types you'll see out there. The batch inference pipeline is one that runs on a schedule, maybe once. In this case, we're running it once per day. What we do is we get a reference to our feature view. We get a batch of data. In this case, I say, hey, give me all of the data starting from today. So what it's actually going to do is it's going to pull the weather features out that are starting from today. But when our feature pipeline is writing the weather forecast for the next 7 or 10 days. So when I say getting from today, it gets all the data from today. So we get all the weather features going forwards 7 to 12 days. I can't remember how many days it is. So this is our data frame that we're gonna score. We get a reference to our model by basically downloading it and then deserializing it. Typically, if we're using Streamlit earlier on, it'll cache this. And then we just basically call predict on our data frame in this case, because I trained on a data frame, so I can predict on the data frame. And then these predictions, depending on how you want to consume them, or if you want to send them to some sink, you can write them to a database if they're going to be consumed by a dashboard. You can create an image. In GitHub, what I did was I created images, with matplotlib or whatever, Seaborn, saved it as a local file, and then in GitHub Actions, I committed that local file, and that ended up being the image that you would see on the GitHub Pages account. Now, the online inference model it's an online model. That means that we've got an interactive application. The user's potentially entering some data, and we need to featureize that data, and then we need to read up pre-computed features in the feature store, join them together, and then we make the prediction. So in this case, imagine I have the city name coming in from the user interface. There we go back here. And I'm using that city name to retrieve the feature values, the weather for that feature for the next week, and I get it back as a Python array. If I had other features which needed to be computed from the UI, I would pass them in here as other features, and they won't be read pre-computed from the feature store. So then I'm calling predict on and getting my predictions back there, and I pass them back to the user interface. So in this case, it will be the PM5 2.5 values. Now, the other one I'm going to skip over is a streaming. You can have models in streaming applications, like if it's not human facing, but if it's a machine-to-machine pipeline that's taking in events coming into Kafka, for example, and you're making predictions on them and writing them out somewhere else, maybe to another Kafka topic. That's the other one. I'll skip over that. Right, so let's have a quick look at the code for that. Now, do I have Hugging Face open here? I don't. Let's have a quick look. So, Hugging Face says, no, I'm not logged in. Of course I'm not. Oh, I remembered something. This is a miracle. OK, here we go. Air quality. So I got a bunch of them here. So I actually did this earlier. I was just messing around. So what it's doing here is you can see it's connecting, blah, blah, blah. This is running the program. So the program is actually in here. This is Hugging Face Spaces, if you don't know. Like I said, it's free. You get 16 gigabytes and 2 CPUs for free, which is what their 150 million in VC money is being spent on. Thank you very much. But basically what I did was I was very lazy. Normally you would clone this repo and then update the data and push it, but I hadn't registered my SSH key, so I was just like, I just uploaded the files. You can do it in the UI. You can just like click add file and uploaded them. So this is my inference pipeline or program here. It's basically, it's an online inference program, but it's not using the online feature store. It's actually just going to download the model. So this is it here. So what it does is it's using Streamlit to print out this stuff that we saw there. It's going to print out getting the feature view, getting a batch of data, downloading the model, and then this is plotting the model and making it look nice, downloading the set of cities to open that we're going to make predictions with, and connecting to the feature store. So it's basically kind of stuff we've looked at already. And then there's also some support here because you can click on the map to select the cities you want to predict for. So that's in there here. But it's all just pure Python code. So you can do these UIs in Python, and it's not particularly intimidating, if I'm to be honest. And then you press this button that we saw earlier. And this is it here where I can make my predictions. Remember, this is where we select our cities, and this is where it's like, connecting and showing some of the data. This is not the world's best UI, but there are loads of better ones out there that you can check out. So it's pretty straightforward to do a UI in Python. Like if you're a data scientist, and when you show off your model to your boss, the value that this gives to stakeholders compared to just showing the F1 score is enormous. If you're going to do recommendation system, or if you're going to do churn, if you're going to do whatever type of prediction problem you're dealing with, allowing them to play with it and to maybe try different values and see how things work, gives them a much better insight into the value that you're adding with your machine learning. That's it, right? That was our three. So an ML system is 3 parts. It's the feature pipeline, training pipeline, the inference pipeline. You put them together. You don't build the infra. Just use these existing serverless services that are out there, and you can build full machine learning systems. So if you've built your system and you're happy with it, then you've got into the boring part of what we call ML ops, which is how do I operate this thing and make sure it keeps running? Because you want to make it better, You've written a program, you're happy with it, and you say, look, it's nice, but then you got an idea. Geez, I can, that other feature, if I could add that one, it would be great. So all ML-enabled products will evolve over time. The available input data that's there will change. The target trying to predict will change. ML ops is not about Kubernetes or Docker or Jenkins, right? Now it is about, however, being able to move faster while not breaking things. So not doing the Facebook way. So basically saying we want to iterate as quickly as possible, but I want to be confident that the changes I make will not break stuff. So you do have to care about testing. You have to care about testing. And if we think about testing, it's really a pyramid. So testing is very much a pyramid, and we'll look at it in a second. The other thing that you need to care about is versioning. They're the 2 building blocks of ML ops, are versioning and testing. So we need to test features, we need to test models, because our models are being built on features, and if the features aren't being tested and the features are broken, well, then we're not going to have good models. And if we're building AI-enabled applications on models, the models need to be tested. Otherwise, the ML applications might be broken. So it's really a pyramid, and these tests should be run as part of the CI/CD workflow, but you don't necessarily need to learn Jenkins to do it. You can use, there's plenty of other tooling out there that's easier to get started with. So ML systems are ultimately built from raw data that we necessarily is not trusted. We may have logic for our features. We can use PyTest to compute unit tests for our features. We can use great expectations we saw earlier to validate the data. And once we've tested, once we've tested these features and we've validated the data, we can pass it on. The models can now, with confidence, be trained and say, okay, this model appears to pass all our validation tests. It's good enough. We can pass it on then to the app, and the app can test that model versus the previous version of the model with an A/B test or blue-green test. And this is basically how we build these systems. Now, The other building block of ML ops is versioning. And versioning is not as obvious a part, right? But it's not something that people talk about too much. So in machine learning, we don't talk about data in general, right? We have ML artifacts, right? So the ML artifacts that we care the most about are the features and the models. Now, there are some intermediate ML artifacts, like you have a training data set, which is a snapshot of feature data. You know, the models are obviously going to be immutable, but the features coming from the feature groups, that's not immutable. They change over time. There's new features added. And in MLOps, we say that, hey, I have a new version of my air quality model, and it's going to be much better. It's going to be air quality version 2, right? It's like, what did I do? Well, I found some new air quality data, and it's better quality than the previous one. And I can't mix the old feature data with the new feature data, because then my models will be terrible. So I'm going to create a new version of this feature group, air quality v2, and the old one will stay there. I'm not going to throw it away. But I'm going to train my model with this new v2 and use the weather features in v1. That was fine. So I get model v2, I press upgrade, and now model v2 is going into production. So the kind of problem you can have, of course, is that there's a problem, right? So you want to roll back. So how do we do it? First, we upgrade. Everything's good. So if you want to define MLOps in one word, I would say it's the big red button. That's not one word, is it? Sorry, it's 3 words. So if you have a big red button where you can roll back any changes you make, that is nirvana, right? Then you can basically say, hey, I'm confident to deploy new models because I know that if I deploy it, I can always roll back to the previous version. But we saw that models are connected to features. So models need the features from the feature store, and they need version 1. They don't need version 2. Version 1 of the air quality model only uses version 1 of the air quality feature group. So we need to keep them around, the features and the models, until eventually we say, OK, I don't care about air quality v1, but now you need to get rid of both the feature group and the models, and then you can't roll back. Now, I did mention that MLOps is not about Docker or not about Kubernetes or cloud infra, but it is about testing. And testing, MLOps does come from DevOps, and the basic principles of DevOps are successful for building reliable systems and being able to iterate faster, being able to make small changes and deploy applications every few hours. That's been quite revolutionary for application developers. And the same should be true for machine learning. If you write enough tests when you're training your models, sorry, not training your models, but when you're also creating your features. So if we have some unit testing for our features, and I'm writing them, and I run those before I create a PR in Git, push them to my staging feature store, and then it'll do a pipeline run and make sure the pipeline runs are OK, have some subsample data, make sure the data validation rules are OK, and then I kind of push to production, and I end up with an orchestrator. So the 3 pipelines that we talked about, feature pipelines, inference pipelines, and training pipelines, they will need to be orchestrated. So it's not enough just to orchestrate a feature pipeline. You'll need to orchestrate a batch inference pipeline. Probably your training pipelines will need to be run on a schedule as well. Sometimes you'll need to backfill data as well. You say, OK, I need historical data. Let's run a production job to backfill it. Models, when you're doing CI/CD for models, the kind of things that I find is really useful is to have a subsample of data in your GitHub repo. And what that means basically is that, sorry, you don't have to actually, but it means you can train your models faster. But like one of the things that's very useful when you've trained a model with the feature store is that it's very easy to create what I call an evaluation set. So typically we know that we should evaluate our models on holdout data sets, a test set. But if you evaluate your model on just the test set, which is representative of all the data, then maybe your model has good enough performance, so its accuracy or loss is good. But maybe there's some subgroups where the model's biased against, right? And maybe you know in advance what those subgroups are. It's gender, it's ethnicity, it's whatever. It's geographic location. Wouldn't it be easy if you could just create those subsets from the test set and evaluate your model on all of those different subsets, or what we call evaluation sets? And now you can see if the model is performing similar on all of them. And you can even automate that by checking the statistical difference between the model's performance for those different groups. And that's where a feature view, you just basically say, hey, create test set, and then filter on whatever you want to filter on, whether it's gender or ethnicity or whatever you want to test for bias against. Okay. Yeah, and then finally, when you've deployed a model, there are, a lot of people deploy models on containers, on Python. They like fast API. It's great. But there are like model serving frameworks, like this is Kserve here, but there's also, Databricks have one, and there's SageMaker. And they give you nice things like A/B testing, so what's called blue-green testing. So you can have your model in deployment, and then all the traffic is going to that, but 10% of the traffic is being sent to your now the green model, the one you're testing. So you'll see the performance of it. And if it's working well, then you can increase that 10 to 50%, and then 100%, and then switch the traffic to your new model when you're confident. So it's great to have these kind of capabilities to build really production machine learning systems. The other thing about MLOps is that when we have versioning and testing, we often have to debug systems. So we want to log the predictions, we want to log the features, and we want to also be able to go up and down the stack. We want to know this is the prediction made on this model deployment. What model did it come from? What feature view or training data set was used to train that model, and what feature view did it come from? What feature groups did that come from? So this is very useful in being able to debug problems in your systems. Another thing, just in terms of logging, I mentioned we have encoded feature data and non-encoded. You typically want to log the unencoded. And that's why it's good to do the encoding in the inference pipeline. Because if you're doing your encoding in the feature pipeline and you're logging in the inference pipeline, good luck in being able to understand what's happening if you've normalized your numerical features or one-hot encoded your categorical features. It's going to be hard to debug any problems. And then for versioning, like if we just take how do you do versioning in a platform like Hopsworks, well, you can basically create a new version of a feature group. And a new version of a feature group is a schema breaking change. Adding new columns is not schema breaking. If they have a default value, that's fine. But if you want to drop a column, or if you want to change how you've got this embedding, and the embedding algorithm sucks, I'm going to change to a new embedding. You can't mix the data from the old embedding, the old feature data, with the new one. So you need to create a new version of your feature group. Sometimes you have to backfill them with these existing data, but there are some optimizations you can do. You can create a new feature group with just the feature that you want, new feature you want, and then you can create feature views that join it with the older versions. So that's it. We've got a couple of minutes left, but that's good. I always like to finish a little bit ahead of time so you get a rest. But what are your ideas? Have you got any ideas for serverless ML systems? We've talked about how to build them here. How to write our 3 different pipelines. But I found this. I mentioned the course ID 223 at KDH, and there were 96 students in groups of 2. So there was like 48 different groups. And I said, look, here's the air quality project. Go ahead. And I gave them some of the code. I gave them the basic code for it. So the feature pipelines. I said, go off and build that. But I would prefer, if you want to get an excellent grade, you have to come up with your own prediction problem and get it approved by me first. So there is a website with tons of them. I'll actually be able to find it here because this thing is kind of working. ID 223, here we go. And just to give you an idea of some of them, we have football betting predictions, Bitcoin price predictions. I mean, they're kind of easy enough ones. Removing voice from songs, which is pretty cool. House price predictions, everyone cares about. Ski snow depth prediction, which you might think is just totally correlated with weather. But it actually, at the end of the season, it's hard to predict, when will the snow get too low. So it depends on sunlight as well as temperature. Electricity price prediction. There's one in electricity price demand in New York, predicting crime and SF. That's not hard. Don't know if you need to do that. It's high. But yeah, so you can see there's a lot of links in here. If you Google this, you'll find it. I think it's covered in some place. Here's another cool project that we did. It's a lab, actually. It's really straightforward. We use Whisper. So if you're not familiar with Whisper, Whisper is a pre-trained model by Hugging Face that can transcribe text. So it transcribes audio. So of course, we come from all over the world. So what they were able to do is fine-tune the Whisper model for their language, their mother tongue, if you weren't Swedish. Someone did it for Swedish. And so then, in fact, the notebook we used by Hugging Face, what it does is it needs a GPU, so you run it in Colab. The problem is it spends 45 minutes computing features, and you do not need the GPU for that. Now, any of you who know Colab knows you get like 90 minutes in Colab before the GPU's like pulled from you. So most of the time, or at least half the time or more, is not using the GPU. So what they had to do was break up this notebook into a feature pipeline and a training pipeline. So the feature pipeline ran for 45 minutes. It outputted then the encoded, in this case, sound data they were going to fine tune with, and they stored it into Google Drive. It was about 15 gigs. It just fit in everyone's Google Drive. And then you could use, some of them use Hopsworks, but I think Google Drive is good enough as a feature store in this case. And then you had a training pipeline. So in this case, if you want to do really good, they'd have to save the weights, and you would save the weights because Google would yank the GPU from you. Then you can restart the training from your saved weights. Here's the kind of things people were doing. This is back in November, October. Here's this is a cat, so you have to say in Swedish the word cat, which, funnily enough, is cat. And it will tell you if you said it correctly or not. And it does banana, which is banan. And you have to kind of guess that. So other ones were taking Swedish language and transcribing it and then chaining it. So translating it into English. Others were doing, at that time, ChatGPT to summarize text. So it would take a podcast, and then you would transcribe the podcast, and then you would run it through ChatGPT to summarize the text. So there's a lot of really cool stuff you can do these days. And these are the first Galician language transcribing systems in the world, and even Swedish. I think that's pretty cool. And it's not hard, right? This was like literally a 10-day lab that they had to do. So hopefully that'll motivate you a little bit that this is not something that's too hard out there. Here's my idea, stupid idea. Personalized GPT-4, ChatGPT. So the feature store will give you history and context. You can have a vector database to give you like handcrafted prompts. If I'm doing a churn model, ChatGPT doesn't help me too much. It says a churn is this, But what if I had all the data about your customers? I knew about your customers. It's in the feature store. I knew the amount of churn. I knew the amount of products. And then I have a vector database with some nice handcrafted prompts. Then it would be great. Then I could have like a personalized ChatGPT. That's the kind of thing you can do. It's pretty cool. Ideas aren't worth very much, but they're worth something when you implement them. So if you want to learn more about this, we do have a community. It's a very nascent community. Like it's about 1,000 people on the Discord. Please give us a star on GitHub if you thought this was interesting. The course is out there already. I'll do a new version of the course probably with Modal and Hugging Face at some point this year, if I ever have time, which I never have, but that's just the way it goes. So that's it. And any questions? Thank you.